Thank you. Given, so I've given a lot of talks, just making sure how many of you have been in my talks. So there is not much new stuff. And how many of you have been in PFAS talks? And there have been a lot of PFAS talks, so just making sure that everyone is aware. But I will still give mostly overview and talk about how we are trying to address this. So, how many of you know about Bangladesh? Yeah. I come from Bangladesh, which is a very, very tiny country. 1.3 times. It's not one. I need to change this. Like 1.3 times of Nebraska. It's not. Nebraska is 1.3 times of Bangladesh. Actually, it's the opposite. And then, but the population is 90 times of Nebraska, which is crazy, right? It's 180 million Nebraska. Yeah. So you can understand there is like the population density is one of the highest in the world, which creates a lot of problems and water problems. So I did my bachelor's in chemical engineering in Bangladesh, and then I moved to South Carolina, did my master's there, and then PhD in Austin, Texas. Then I was a faculty for 7 years in the University of Buffalo. That's when I understood what is Great Lakes, and then I moved to Great Plains, which is kind of interesting. So, and this is my lab group right now. We have several PhD students. We do research on environmental nanotechnology, mostly understanding how we can use nanomaterials for water treatment. This is my lab group. So now we do a lot of fostering. So this is some of we have a lot of beds of our own, and then some fostering. So currently, I have 3 PhD students. Just graduated one master's student. Then I had a postdoc for half a year last year, and I graduated 3 PhDs. Most of them actually contributed on the projects that we have been doing. There is a lot of undergrads that worked in a lab previously. So this is our lab facility. If you haven't been in our campus in City Campus, this is the environmental engineering lab. We have a shared lab. We don't have individual labs for all the faculties. 5 of us to share the facility. We have a process lab where most of the wet chemistry work happens. Then we have an instrumentation lab. We don't have super fancy facility like Dan has, but we have some. We have an LCMS where we have developed a method for PFAS analysis. We have a GCMS and some analytical capability. Not a lot, but we take a lot of it from WSL. So how many of you are familiar with nanotechnology and nanomaterials? Okay, how many of you use nanotechnology? Not everyone? How many of you use smartphones? Everyone. Who are from this time frame? Nobody. When the first computer was like the size of this room, right? And then we have now smartphone where we can see and do a lot of things together. So the main thing about nanotechnology is that it's called nano. It's very small. We are talking about scale of atomistic or molecular scale materials that are solid materials. Basically, they're not necessarily chemicals. They are solid particles that we deal with, and solid materials that forms the basic fundamental parts of electronics. Okay, so if you look at the first transistor back in 1947, which literally created electronics, and we went from analog to digital, from electrical to electronics. That's the size of the first transistor. And in an iPhone 16, we have 16 billion transistors. So you can imagine like how we went from that size to, I cannot say, it's very, very small size. of material. So we have 16 billion transistors in iPhone 16. So who can guess how many transistors we have in iPhone 17?
17.
17. So iPhone 17 has 17 billion. I don't know when this will go down, or if we can keep up with that technology size that the numbers of transistors will match with iPhone number. There is a physical limit at some point. But this is what nanotechnology gives us, is that we can manipulate material or design material or create material at nanoscale atomistic level. The main difference, I say, that nanomaterials are, just remember that they are not chemicals. For example, these are solid particles. If you think about sugar or salt, when we put sugar or salt in water, they completely dissolve and we cannot see under electron microscope even individual particles because they are totally miscible, right? When we take sand particles, for example, if we grind sand particles and put them in water, even if we grind them in the smallest scale, they are still solid particles. They are not dissolvable in water. So they can remain suspended in water, but not dissolvable. So that's the basic difference, I would say, that you can think how we differentiate between nanomaterials and chemicals, because both are in molecular or atomistic scale. And we can create different types of nanomaterials. They can be carbon-based. You can think of graphite, the lead of pencil, right? They are multiple carbon layer structures. So if we, but pencil lead is graphite, which is an insulator. This doesn't conduct electricity. But if we take out one carbon layer of that graphite, if we can take them one single layer out and keep it independent, so the electron that was binding these different layers of carbon in graphite, that becomes free, and that can move on the surface of the graphene very freely. What it means that it becomes, so graphite, when we can create graphene from that, it becomes electrically conductive and highly conductive. So from graphite to graphene, we go from insulator to a highly conductive material. And that's the second difference, that it's not only that we are trying to create materials in small scale, but that material in small scale will provide properties that are not achievable in bulk scale, right? So that's the thing. So we can create a lot of, like, these are some of the examples, very few, because we can thousands and thousands of different types of nanomaterials. Either they can be carbon, they can be metallic, they can be carbon and metallic together, they can be polymeric. So, and we have used polymeric just for curiosity. I don't know if I'm supposed to listen. Anyways, many of us got COVID vaccine. Okay, so the COVID vaccine was possible because of polymeric nanoparticles. Because the idea was that the virus RNA that was used to create the vaccine that needs to go inside our body, and how we deliver it to our body is we package it inside of organic polymer nanoparticles so that it doesn't degrade on the way to where it's supposed to go. Okay, so that's how nanomaterials actually nanotechnology tackled a global pandemic. Okay, so those are different examples. So this is another example. If you think about gold, gold is inert in environment, so we use it as a currency because it doesn't really degrade in natural systems. But if you think about it, there is not much of functional use of gold, unless you want to make a Trump Tower. But if you think about when we go into nanoscale, and if you look at these examples like nanorods, we can create like these shapes, different shapes. We can create a shell around another type of material with gold shell. So when we go into that nanoscale, which is very, very small scale, in that nanoscale, when we change size, either aspect ratio, so that is aspect ratio is basically length to width ratio of certain rods. If we change the aspect ratio, if we change the shell thickness, if we change the composition or percentage of gold in a material, that can give us different colors. What it means that they react or interact with light differently, which means that they can be tuned to provide different optoelectronic property. Okay, so that really helps us designing catalytic materials from gold. So what I mean by that, again, bulk gold doesn't do anything. Nano gold can do a lot of things. They can be used in cancer therapeutics too, in some ways. So what we do in our lab is we design different types of nanomaterials and we modulate their properties. We try to enhance their properties for different application. And mostly we are focusing on water treatment, how we can take out pollutants, different types of pollutants from water using nanomaterials. That will, we basically design these materials. But at the same time, like, yes, they are not chemicals, but these nanomaterials are born out of same chemical elements or compounds, right? Their structures are different. So they can also become a pollutant themselves. So there is a major concern. So are they going to be toxic if they are released to the environment? And when we are producing them, if we can get exposed to them, are we becoming sick or will there be an impact? So we also look at their environmental and health impact. So we try to design materials that are sustainable and safe to do water treatment. Okay, so that's kind of like an initial and view of our group. So what we are trying to do at the core, we try to use nanotechnology for water quality engineering, but we try to use them sustainably by doing safer design. We are trying to also use that whatever technology we develop in our lab, can we make it actually applicable for larger scale? Either is it for point of use water treatment or in drinking water or wastewater treatment plant. At the same time, we are now working with artificial intelligence and machine learning to find which materials we can design in a better way, or which property will be used, or what type of nanomaterials can be used for what type of contaminant or what type of water sources we are trying to also find. So there are a list of different things you can use nanomaterials and nanotechnology to do water treatment, but one of the major things here highlighted is emerging contaminants, and that's what is PFAS, right? PFAS is known as an emerging contaminant, and emerging contaminants, now I'll be switching from nanotechnology to totally into emerging. So that was kind of like introduction of what we do in our lab. But emerging contaminants are not necessarily, they are emerging in the sense that they're coming out now, but actually we are finding them now, okay? For example, PFAS, then pharmaceuticals, different trace contaminants that we are trying to find, because now we have new spectroscopic technologies, right? Liquid chromatography technologies and analytical instrumentations that enable us to detect very small concentrations of chemicals in environment. And that's when we are finding these chemical contaminants, which we couldn't find before, okay? That's why they are emerging. Emerging doesn't mean they are coming out now. We are finding them now. That's why they are called emerging contaminants. And we work with different colleagues in different projects. Our projects are funded through different agencies. Like we have collaborators in multiple different places, obviously within UNL, but also other places across the country. So how many of you have watched this movie? Okay. Everyone else watched this movie. So this is from 2019 with very good actors and actress, but you can't find this movie free in any of the portal. Can you guess why? Because somebody wants us not to see this movie, right? It's a good movie. It's one of the best movies I have seen, but it has 3 Academy Award winners in the top, like in the major characters, but you don't see it because it talks about how DuPont and 3M, these are the major chemical manufacturing companies, how they knew about PFAS and its effects on humans and the environment, but still they didn't disclose because it's a multi-billion-dollar business. Okay, so like there was a statement in this movie that is like when this is about the lawyer who actually basically figured out why this is like in West Virginia, how PFAS is impacting farms. Okay, what there was DuPont was throwing these chemical wastes into disposing this chemical waste in near a farm, and the cattle in the farm were dying from drinking PFAS contaminated water. I believe the farmer lost about 200 cattle basically, and then he and his wife also died of cancer. All of them were impacted by that. So that's the story which started finding PFAS. And what is PFAS? You can see all these chemical structures. So everybody here loves chemistry, right? So all the structures that you see, the core of it is this carbon-fluorine bond. Okay, so this is one of the structure that this movie talks about, PFOA, perfluorooctanoic acid. So it's an 8-carbon chain of organic carbon chemical, where you see instead of hydrogen, typical organic chemicals will have hydrocarbons, hydrogen on carbon, but all the carbons are replaced by fluorine. So the fluorine is highly electronegative, and carbon is electropositive or close to neutral, but a little bit positive. So carbon-fluorine bond is very, very stable. It's one of the strongest bond possible, and it didn't exist in nature. There is no carbon-fluorine bond that exists in the universe. So it was created by scientists in DuPont and 3M. And because this carbon-fluorine bond is very, very strong, it can withstand high temperature, high mechanical force, so it can resist water, it can resist oil, it can resist fire. So we use them in many different applications, okay? So we can tune their structures because you can create these chains in many different ways. You can create multiple different carbon structure. You can change the number of fluorine, how they're organized on the structure. You can change all of them, so you can create tons and tons of different PFAS molecules. Apparently, there are 15,000 or more PFAS chemicals possible. So these are some of the major ones that we can see. So this is PFOA, which is 8 carbon. Then there is sulfonic acid group. So if you see here, the end groups are different, either carboxylic acid group, sulfonic acid groups. So PFOA and PFOS are important to understand because these are the two major ones that was created back from 1940s. Actually, during World War II, DuPont and 3M, they created these chemicals because you can coat a surface to make it hydrophobic. So you can coat the tanks that go into the war to make them hydrophobic. They don't rust in water. So that's why they were created. So eventually, because these are so good and resisting water and fire, where do they end up? When we use them in non-sticky cooking pans. Okay? All the non-stick cooking pans that we have seen has a coating of PFAS on it. Okay, that's how, like anything and everything that is water resistant, fire resistant, oil resistant has PFAS in it that we use. Okay, so you can see from raincoats to non-sticky pans to firefighting foams to coffee cups. All the great coffee cups that we use, the paper cups we are so proud of that we are not using plastic. They're made of. They have a coating of PFAS on it so that they don't get wet. So it's really scary. Like this carpet, it has PFAS in it. These electronics has PFAS in it. Okay? So as I said, like this is the newest paper that we wrote. This was an outcome of a workshop that happened in Intel in Oregon. Many of us, faculties, industry, and government agency, we sat there and we learned about how much PFAS is used to make electronic chips. There are hundreds of different types of PFAS molecules. They can be short chain, they can be long chain, they can be volatile, they can be dissolvable. Many chemicals are used in semiconductor manufacturing, and it's a huge issue because nobody was thinking that we are using PFAS in semiconductor industry before. Now we are finding that we use PFAS in semiconductor industry a lot because this CF bond actually makes so many unique things that are not possible with any other compounds or bonding. So it's very interesting. Now we are finding them in semiconductor industry too. So they're ending up in our wastewater. So how are we getting exposed to? So we get exposed to this PFAS in many ways. Through food, because this PFAS is going in our wastewater, to drinking water, it's going into the aquatic systems, the fish and aquatic organisms, they take it up. Then we get from food, then we get from drinking water, then we get from exposure to anything that contains PFAS. And then they can, I think there is another. Yeah, so these are like different ways how we can get exposed to PFAS through food, through drinking water, and dust exposure. These are multiple ways that we can get exposed to PFAS. But at the same time, what are the problems? They can cause a lot of different health issues. What happens? PFAS is in very, very small amount. They go inside our body, but PFAS is carbon-based. So the major part of the chain is carbon-based. And they are hydrophobic. That part is very hydrophobic. So they don't want to stay in water. So when we are drinking water, and it has PFAS in it, the PFAS doesn't want to stay in the water. It goes and attaches to our body because our tissue and the whole body is made of carbon. So there is a hydrophobic interaction that goes in, and we start building up of accumulation of PFAS inside our body. And over time, through this chronic exposure, because they go and attach to our DNA or cells or tissue, they can start to create cancer. Because all the cancer cell is basically mutated cell, right? So that's how cancer starts. So there is a lot of evidence that there are multiple different cancers that exist because of PFAS contamination. But there are other things too, immune deficiency. Vaccine doesn't work if you are affected by PFAS. Then in like children, like even there are stillbirth situations, there are low birth weights, there are multiple different issues. There are neurodevelopmental diseases that happen to children because of PFAS. So there are many different ways we are getting affected. But where is PFAS in water? So in most cases, in environment and water system, what happens? We use a lot of PFAS containing products. From there, many ways PFAS end up in our wastewater. Okay, municipal wastewater. Municipal wastewater. The issue is that in the water treatment system, wastewater treatment system that we built, they are not capable of taking out PFAS from water. We were not designing it for PFAS, so it's a major problem. So many of them end up in the surface water, going up. But a majority part, because they are hydrophobic, in case of biological wastewater treatment, we have a lot of bacteria loading there, which is also carbon-based. So they create a lot of solid sludge, okay, in municipal wastewater. So that solid sludge ends up containing a lot of PFAS. Now, the solid sludge or biosolid is used as fertilizer in many places because they also contain a lot of nitrogen, phosphorus, a lot of different nutrients that are really useful for farms. So 95% of Nebraska's biosolids end up in farms. Now, there is a possibility that these PFAS containing biosolids are going to leach PFAS either to the plants and soil, and they will be taken up by plants and kettles in many ways. So the state of Maine has banned any biosolid application in land because there has been incidents of significant amount of plant uptake and food contamination because of PFAS and issues because of PFAS. In Nebraska, to our understanding, the contamination situation is not that bad. Okay. Maine and Northeast, like New Jersey, Maine, Minnesota, these places, they had huge PFAS manufacturing plants or nearby PFAS manufacturing plants from where there might be contamination more compared to how we are getting this contamination. Okay. Because many times the industries and municipal wastewater treatment get both industry wastewater and municipal wastewater, right? So when they're all combined, you can, depending on what type of manufacturing industry you have, that can have a lot of PFAS versus some cases we may not have a lot of PFAS. So the problem is not only in water, but it can also go to different type of food. There was a study last year that showed how much PFAS is in milk that we buy from grocery store. And it was interesting because they tested they took different cartons of different brands and different cartons. So the ones that were organic, they showed 3 in 10 cartons to have PFAS indetectable. The ones that were not organic, regular ones, they had 1 in 10 cartons to have PFAS indetectable. It doesn't mean it's toxic or not, it's just detectable. We can detect that there is enough PFAS that even with a trace amount of PFAS, we can detect them. That's because it's very hard to even detect very low amount of PFAS. So this is a study, this is a news that came out in New York Times. New York Times actually did, that was back in 2024, September. They did a series of stories that talked about PFAS contamination. So this was the first one. And this is an example of cattle calf, stillborn calf that was found in a Texas ranch. Then this cattle calf was taken for testing, and its liver was full of PFAS, which was about 600,000 parts per trillion. How many of you are familiar with parts per million? Okay. How many of you are familiar with nitrate problem in Nebraska? So there is a limit, regulatory limit of nitrate in drinking water. Anyone knows what is that limit? 10 ppm, parts per million, right?
Pretty high though, that's not the normal amount.
Yeah, so that's 10 parts per million, right? So if we divide by 1,000, that's parts per billion. If we divide by 1,000 more, that's parts per trillion. And we are talking about 600,000 parts per trillion. So if you think about it, this is 0.6 parts per million. That doesn't sound so bad compared to nitrate, right? Nitrate is 10 parts per million. So if we look at what EPA said in 2024, if you look at this, like this is, they said the maximum contaminant level for PFAS. The first two are PFOA and PFOS. These were the major two ones, that were produced most previously, but these two are banned now for production. So their limit, maximum contaminant level, is 4 parts per trillion. And if you look at this one, this column, maximum contaminant level goal, which is 0. What does that mean? Why do we say MCL 0?
There's no safe level.
There is no safe level. That's it. So if you think about it versus if we go back, it's 600,000 parts per trillion. It's really crazy, right? So they couldn't figure out what really happened. One of the ideas is that wherever this ranch is, they probably have a nearby contamination zone from where water is coming, or the drinking water that are fed to the to either they're getting from food, grass, or anything, or they're getting it from drinking water that is the cattle are drinking. Okay, so it's not only human health issue; it's also like ag and food issue. So EPA came out with these regulations. They wanted to say that, oh, we will control PFAS exposure through drinking water. Now there is a catch. PFAS exposure doesn't only happen because of drinking water to humans. It happens in multiple different ways. Only 20% of this exposure happens because of drinking water. But that's the only one the government probably can control. Because the other ones are coming from food. We don't really control food, right? It's about habit. Who is eating what people can afford based on that. So EPA decided, okay, we will control drinking water. They came up with this list of PFAS chemicals that thought these are the priority ones that we should control, and they set a very small limit. First thing, it's a great decision. You can control this. Second problem is that most of the water treatment technologies cannot do this, current treatment technologies. So you have to upgrade all the water utilities to have new technologies in them to be able to take out PFAS. To do that, we'll have about 200 billion or more costs across the country to do this. Who pays for this? Users. We pay for this, right? So what happens then? If we pay for this, there should be a new rule, right? Because we are not polluting it. Many of it is coming from industrial waste. So the next step EPA was going to do, I said, what I'm going to do is to set up a wastewater limit for PFAS. Okay. And that was almost there. It was in the White House for review. And then the government changed. What changed with the government change? That review is no longer needed. That regulation was not anymore set up. What eventually happened, the US EPA came back, the new US EPA, the new administrator came back and said that we don't even need to control these 5 or 6 that we were targeting. We only need to control this 2. Okay? And now they are saying, it's good that we are controlling, but we need to be careful about how we are setting these limits. We need to reevaluate them. And we don't know what that means. If we make it high or low, then you cannot go lower than this. It's 0, right? So it will be becoming high. So it's a lot of things that is changing with EPA. Right? The whole EPA Office of Research got dismantled. So that's a very different issue. So, but overall, there is a lot of issue to deal with. But one of the good things is that the states, many of the states, are already taking actions. And they realized, okay, the federal government is probably not going to do anything for now. We have to do our part. So they are still doing their part. Many states, actually, New York State, they have much higher. They had PFAS regulations even way back, like 5 years before EPA came out with this regulation. So their limits are even lower. Okay, so this is a map. This is a website, Environmental Working Group. They have a website, and you can go to this website and check actually where PFAS contamination is there. So you can just write up EWG PFAS map. This is very interactive map. So if you search with Nebraska, it will show PFAS in Nebraska where they are. And if you look at the regions, so there are drinking water, then some groundwater. So the third one is that military site? Yeah, military sites. So if you look at the purple one, so that one is military sites. So one of the major sources of PFAS contamination is in the military, Army, Navy sites because they have been used as firefighting foam. So any explosion, any explosive training that happens in defense, PFAS has been used for many, many years, and they are used in huge quantity because the explosions are very big. There is a lot of fire. So the highest contaminations are in military, Navy, or Air Force bases. Okay, if you look at Nebraska, where is the most contamination? Anyone knows? Any military places nearby? Offutt Air Force Base. Okay, that's where the groundwater and soil concentration is very high, and that will be in the ranges of thousands per trillion, like 20,000, 40,000 parts per trillion, which is a major issue. So, interesting fact. So, Department of Defense was the major funding agency who was funding PFAS research for the last 25 years. They were the first ones to be concerned about it. This is the first year there is, in their proposal call, funding proposal call, there is no mention about PFAS. It's a new APA, it's a new DOA, so we don't have to think about contamination anymore. They're gone, right? Okay, we have about some time. Okay, so that's the problem. Now, how do we solve the problem? If we, yeah, go ahead.
So the map that you just showed, there's big open areas in the Great Plains and Middle West, but is that because there's just not much testing and so we don't really know what's there, or is it where our levels are?
So most of these testings are not like, if you look at it, drinking water, right? Drinking water, military sites, other known sites, right? Drinking water and military sites, if you think about it, drinking water is being tested where people are. If there is not much people, there is not much testing. Actually, drinking water testing happened. Dan can also. USGS did a lot of drinking water monitoring. US EPA does a lot of drinking water monitoring. So this is like UCMR 5, which is 5th unregulated water monitoring. So UCMR 5 is like monitoring all the drinking water sources, but that doesn't count the private wells. It's just the ones that are publicly owned, either it's state level, city level. Those are the only ones that are monitored. So if there are private water sources, those are not being monitored. Some people are getting anxious and they want to know, so they are reaching out. But the problem with PFAS is it's very expensive to test. So again, comparison to nitrate, you can take a test strip for $10, you can test it. PFAS, the minimum cost is, then minimum cost is
The
for
cost?
PFAS.
Is that what you're asking?
Yeah,
$600 a sample.
$600 a sample. So good luck with that. Yeah.
I think the USGS has a map they just presented today that if you are looking at streams that receive municipal wastewater or industrial wastewater, I think the map is going to change. These guys have not done that. So
Yeah,
especially in Western Colorado, they are showing a map today that has the PFAS. Yeah.
that's a good one. Yeah, USGS actually came out with a paper, science paper last year. Yeah, about that. EWG is not necessarily, they don't do any testing. They are just compiling data from many different sources. They just built a
Public
website,
domains.
public domains, whatever information that is out there. They're just creating a map. But the map is really good just for looking at it and understanding what is happening. So now we have to treat PFAS. So one of the things is that if we think about the minimum thing that we can do is take out PFAS from drinking water if we want to be safe, right? So separation of PFAS is one of the main thing, right? How do you separate PFAS from water? The second thing is destruction. As I said, like the carbon and fluorine bond. So if you separate it out, then you concentrate it, but it has to go somewhere. It's kind of like nuclear waste. Okay. So PFAS, the thing is that nuclear waste, oh, you have taken it out, but you have to put somewhere. PFAS is same, because now if you put it in landfill, they can leach out again and contaminate other places again. It's not that all the landfills will be like that, but there is a possibility. So there is another part that is a major concern is destruction. If you don't degrade that carbon fluorine bond, then you still have the PFAS in hand. So it's kind of like the poison you have in hand. So there are many different technologies that are being tested. So one of the major problem, like if you look at here, so low efficiency but low cost. Okay, so one of the thing here you will see biological on the left hand side. Biological treatment is like we want synthetic chemicals to be broken down by microbes. If that is possible, you can use microbes at very low cost, and biological treatment processes are very efficient in degrading. With PFAS, the problem is the CF bond, carbon fluorine bond, didn't exist in nature. So microbes never saw it. Bacteria never saw it. So they don't have the capability of breaking them down. So that's why, so if biological treatment was feasible, that would have been the best possible thing for us. Okay, that would be the cheapest. But if it's not possible, there are many different ways. Many of us use reverse osmosis in house, right? Reverse osmosis essentially can take care of most of the PFAS. It has the lowest, it had the highest purification technology. So, but reverse osmosis at large scale, if you want to set up one reverse osmosis treatment plant for Lincoln or Omaha, it's not possible. It's super expensive because it requires high pressure. So membrane technologies like nanofiltration, reverse osmosis, they're not bad, they're good, you can take out PFAS. Then ion exchange resin is another one that can take out PFAS. Granular activated carbon, these are also can take out PFAS. But with granular activated carbon, which is basically, if you think about Brita filters, right, that we use, granular activated carbon is just that the black carbon powders in them. That's what is in granular activated carbon. The problem is PFAS, the good thing is that they can, because most of the carbon based structures can get on the surface of the granular activated carbon. But with the PFAS concentration as high as in New Jersey and Northeast, the problem is you have to regenerate that media, filter media. So granular activated carbon regeneration is very costly. So you have to throw it out. And every 2 weeks, in many cases, in every 2 weeks, you have to replace the whole granular activated carbon media, which doesn't happen for other contaminants. So this is a major problem. So that's why it's not that it cannot be solved, but there are many different problems. So if we look at, in short, so effective treatment technology, granular activated carbon is one, then reverse osmosis membrane is the other one. So they are good, they are more effective for long chain PFAS, like the PFOA and PFOS, they're really good at that. But if there are short chain PFAS, and short chain PFAS, there can be 4 carbon chain PFAS, 5 carbon chain PFAS, 3 carbon chain PFAS, which are not as hydrophobic as the long chain ones. They can be hydrophilic and they cannot be removed easily by GAC or reverse osmosis. So, and also it depends on cost, how much cost is it. So just looking at, this is like how the treatment plants look. This is like granular activated carbon system. This is ion exchange resins. So these are like really, really big tanks with lots of pipes. And these are reverse osmosis membrane in industrial scale that basically they have water going through them. They have a cross flow membrane. So the pipe is like this. The water goes through one side and they moves on the other side. It's kind of like cylindrical membrane, like here. So they're a cross flow membrane, they're called. So they go through here and the PFAS gets trapped in the membrane. So one of the major problem is that PFAS treatment residuals. So, okay, we have given you clean water, but what do we do with the media, either the membrane or granular activated media that has PFAS in it? Now we have to landfill it. Now PFAS is declared hazardous waste. Problem is now the landfills don't want to take PFAS contaminated stuff. because it's a waste. So you have to figure out to not create waste. So that's where my group works. We are trying to create nanotechnology where we can destroy PFAS, not only separate, but also destroy. How do we do it? So this is one of the first works that we did. You have graphene. And graphene we talked about. Graphene it has high electron transfer potential, but it's also carbon, so it can attract PFAS on the surface. At the same time, we can add different types of metals on the surface, which can be reactive. We use iron in this case, iron nanoparticles in this case, which can act as a catalyst. The catalyst, what it does is basically breaks down hydrogen peroxide, which we can supply. Hydrogen peroxide is an oxidant, and it creates these highly reactive hydroxyl free radicals. And these free radicals can react with PFAS or other organic contaminants to break them apart. So that's what we try to do. And we do this, these are lab scale tests. We take PFAS solution with nanoparticles in vials, then we shake them with hydrogen peroxide and without hydrogen peroxide, and then we separate them out just to have the water with PFAS in it and measure concentration after separation of PFAS, how much PFAS is getting separated and destroyed versus how much PFAS is remaining in water. So this is an example, like basically what we found in this work is that we could separate out PFAS from separate and break. So what we saw, we use like PFOA or PFOS. When you use them, then they degrade somewhat, they release some fluorine, then they release some carbon, but they don't really degrade totally. There is still from 8 carbon to we reach to 6 carbon or 7 carbon, but they don't degrade totally. What we see that overall we reach a very high amount of removal, but not total degradation. But we see some degradation, which is really good. And so we try to figure that out. The next thing we tried is once we see that the iron does some good work, it does break down a little bit, but it doesn't really totally degrade. Now we are trying to do, what we try to do is use another material called titanium dioxide. Titanium dioxide, you may not know, they are very, very common. You use them in paints. All these wall paints that you see, they have titanium dioxide in it. The reason they have titanium dioxide, because titanium dioxide can react with water and react with water under UV light or visible light, and they can create, again, hydroxyl radicals or different types of free oxygen radicals that react with different types of organic chemicals and degrade them. The reason they are used in paints, because we don't want mold happening on wall or any place, right? That's why they are used in paints, because they can react with light, interact with light, they can create this reactive oxygen species, and which can degrade or kill bacteria or fungus or other mold giving material. So we are using that titanium, putting it on graphene, and we are trying to see if we can use that under UV light or visible light or under solar simulator to see if we can destroy PFAS to create break down the carbon fluoride bond and create fluoride. Okay, so we have been very successful in it, and because we don't have time, I'm just giving you the concepts, what we are trying to do and how we are trying to do this. There is another way. So I said reverse osmosis is very expensive, right? Energy cost is high. So what we are trying to do, and reverse osmosis only can do separation, it doesn't degrade PFAS. Now we have seen that the nanomaterials, reactive nanomaterials or catalysts can degrade PFAS at the same time. So what we are trying to do, we are taking low-cost membrane that are not reverse osmosis, but we are creating, so these are called ultrafiltration or microfiltration membrane that are much cheaper than reverse osmosis membrane. These are polymeric scaffold. And then on top of it, we are putting very small layer of nanomaterials that are two-dimensional in structure, and you can create this structure, those graphene metal nanocomposites. We are putting them on the surface so that the water can flow through. The PFAS can be on the surface of, can be like blocked on the surface, and then we can degrade by reaction on the surface. That's what we are trying to do in this project. So yeah, so that's what we are doing. And then finally, we have one other project where we are looking at using 3D printing. So if you think about point of use, your tap water that is coming out. So if we want to use these filters on top of it, like right there, instead of trying to treat, if we cannot treat them in the treatment plant. So we are trying to create these 3D printed filters, what we can put there, and that will have similar type of catalytic activity that can absorptive and catalytic activity that can take out PFAS, separate it and destroy it at the same time. So that's one of the projects that we are doing. So I think, okay, one more slide. So this is one of the US EPA projects. So this is an interesting story. This EPA project we got funded in August of 24. Then the new government came. They canceled the grant last year, April. Then in September, they came back and they gave it back. So we are working on it. So this is like, we have the nano technology platform for destroying PFAS, separating PFAS. And we are collaborating with groups in Clarkson University and Stevens Institute of Technology who identify PFAS, who has nanotechnology to identify PFAS in real time. Okay? Because typically PFAS testing is very expensive, very costly. So there is an initiative that was an initiative from EPA to look at if you can design field deployable sensors, nanosensors, and at the same time, can you combine them with the treatment technology? So we are trying to work on that. So we have teams working on sensor, and then our group is working on the treatment or degradation of PFAS. So with that, thank you so much for listening.
So the water that you're using, especially like wastewater outflow, has a lot of other stuff in it too. And how do you deal, like what pre-treatment do you have to do for the water to actually get to the point where you can test for the PFAS?
So for testing
or degrading the PFAS, either one.
If it's about testing, the expert is there.
Right, so there's a ton of filtration you have to do. Yeah, but for degrading.
For degrading, so most of the lab tests we do, we don't really use wastewater yet. We are using deionized water that is very purified. We add things in it. So we have tested in how different pieces, like water has different pH, different ionic strength, like salt, different natural organic matter. And it's not necessarily only in wastewater, it's also in surface water, in groundwater, right? So we have tested with that. So pH has a huge effect. Most of our technology only works at low pH, the ones that we are testing now. And then second, so that means it has to be in a controlled environment. You have to take the water and then control the pH and do the treatment. Second, we had major effect with organic matter because natural organic matter is also carbon-based. So the treatment, if we are taking graphene and then we are trying to do PFAS treatment, but it can also attract the organic contaminants, organic matter, natural organic matter. So that really natural organic matter compete with PFAS in the treatment process. So there are ways to do it. There are some filtration process that you can do beforehand because natural organic matter may be in high molecular weight compared to PFAS in some cases. So if you put an initial filtration that you can take out most of the other contaminants, because PFAS is the hardest to degrade. So you leave it for the end. And that's the same technique that when we went to Intel, they do the same thing. So in their industrial wastewater, they also have like a lot of different things. They have a lot of salt too. So they actually run through membranes, very high efficiency membrane. And then whatever is left, very like, it's only almost like only PFAS or some other contaminants there, but very few amounts. So that treatment is just for PFAS. You have to do that pre-treatment in most cases if you're dealing with complex system.
When I was doing the treatment efficacy slide that you put granular activated carbon in the emerging category.
Yeah, that was for from 3 years back, so. Yeah,
But it's a pretty mature technology.
so I think at that point it was discussed as emerging for PFAS. Not for, this is,
It hasn't improved.
yeah, these technologies that are discussed there, it is like this graph is for PFAS, not for water treatment technology.
Okay.
And I'll say that most of the industry now, because these emerging technologies take time.
Yeah.
But GAC and ion exchange resin, these are pretty mature technology that
Yeah.
you saw the large scale, right? You can put them in scale. It's easy. Even and many places, many cities who have money, they're deciding to go with GAC because
Yeah.
now with the new regulation, you have to only care for PFOA and PFOS. So for compliance, they have to take out just those two. And as long as GAC can work, they are fine with the regulation.
In the future, do you see any regulations on high PFAS containing materials? Like one that comes to mind is Teflon pans. If you think that'll be regulated out, there'll be like more strict standards on how much PFAS could be contained in those.
That will depend on if you're in Europe or in US. The same goes for which state in US you are in. So Minnesota, Colorado, they are having some regulations on which products will be cannot, like which products. I think based on which products contain PFAS, you have to regulate them. Okay. So like for same thing like dental floss. Dental floss has PFAS in it. Okay. Because it's basically Teflon. So that's going to happen. Europe is going for a lot of products like cosmetics, like consumer product banning based on PFAS contamination or PFAS ingredient. FDA just reported that there are 50 different PFAS type PFAS ingredients in different cosmetics.
I
But
think
FDA doesn't regulate anything, so.
we're slowly phasing out products
Yeah.
that contain higher concentrations. And that, these are consumer products and they're regulated in a different way.
But I think it depends on how you say the regulation. Because when we went to the semiconductor industry, and one like the main thing is that okay, the carbon fluorine technology is so unique that if you want to replace it with something new, a different type of chemical, it will take like 10 to 30 years to develop that technology. But semiconductor technology is already there, and they are not going to change that just because we want. Okay, so it's a challenge. So I think still PFAS is going to be there. How we manage PFAS in the waste and how we use PFAS, how conservatively we use PFAS, that is going to be the main thing. We cannot, I don't think we can, get rid of PFAS. And yeah.
Oh, thanks, Sharon. Thanks, Nirupam, for a great talk. I was going to ask, should we be changing our Brita filters more often then?
Sorry?
Our Brita water filters at home, should we change them more often, in your opinion?
I think we have to ask the Lincoln Water Utility if they have PFAS.
I guess that's part two of my question, about the PFAS levels in Lincoln's water supply, or is that off the table at the moment?
The same question I had that Dan, you measured the PFAS in
Water.
Salt Creek.
Well, you measured it in a tap water too.
Then this is a question I was asking Steve when said the Lincoln Water that Salt Creek joins Platte River just at the
Well, that protection area.
so in low flow conditions at Platte River there can you pick up something there?
You could, yeah.
Yeah.
Under low flow.
But it will depend on the treatment. Like if there is.
Yeah, they are just using ozone. That's
But I think to answer the question, just follow the instructions and replace it when you're supposed to.
So Grand Island had an issue, so there was a report on Grand Island water. And they tested with two different companies, it had multiple higher than the regulation. Then Dan and I, like we went there and they gave us the sample and we tested here and then there was no PFAS more than the regulatory level. So they're now very happy with our results, not with the company results. So I don't know what to make of it. Because I think it also depends on when you are actually collecting the sample and the amount is so low that it can go above the limit at some point and some point it can be lower than the limit and it's just few parts per trillion here and there. So
Yeah, like the Sioux City, Iowa, I was there at their treatment plant once. So they are picking up PFAS at one of their wells, which is at the down gradient of location of their runway. And there also 20, 30 years back, there was a plane crash that they just must have put the hell out of these firefighting foam and it all washed off from the runway towards the river. So they were a bit worried 2-3 years back. I was with them. The other question is the Scotch Guard. I heard from some carpet companies they're not using anymore.
yeah, Scotch Guard has been banned for quite a while.
Okay.
Yeah, same reason.
If one thing that the utilities are doing is they're going through and removing any materials that might be releasing these compounds into their distribution system. Grand Island had started to do that too. So I think over time, you're going to see less and less in distribution system and tap water.
I know there's a similar going on in the food processing industry. They're trying to either find new materials or just switch out.
But there are interesting studies about new materials too. They are more toxic than PFAS is. So
No free lunch.
Go back to basics.
my philosophy is the moment humans started doing anything with the environment, we have been doomed. So we're done.
So what happened to the money 3M paid to EPA is fine? Some 11 or 13 billion dollars.
I don't know. Like there have been so many class action lawsuits, and that's why this election was very, very important because I don't know if you guys know, PFAS was one of the items in the Project 2025. So you know where the money went and why EPA and DOD has changed the direction. So
This is more of a comment, I guess, than it is a question. But in regards, somebody back here asked a question about the map that you had shown, and I know I work with the training a lot of water operators and wastewater operators, and they were talking about like it was only a certain population threshold that the EPA was sending tests to municipalities, and so a lot of the smaller municipalities weren't providing those by the EPA. Now the state of Nebraska did provide the free testing. I can't remember what the threshold is. It sounds like some of you guys know a lot about the municipal stuff, but so maybe you know. But so wondering if perhaps, and I know that data for the smaller systems was not public information. It was simply released to the municipality, and so I'm wondering if some of those. It's like I know the Valentine had gotten positive hits, and I didn't see a dot where Valentine would be on your map, and so I'm wondering if that's why we see some of those open areas.
then do you know? But
I saw the map of the smaller cities. I mean, so I think it's semi-public. It's one of those things they're not like advertising it. It was when a state agency does testing. There's some guidelines on like what can be public versus not, but it's still a public agency. So I think that's out there. And I definitely have the map sitting in a paper on my desk somewhere. I can see if I can find an electronic version. It's one of those things I didn't get back to last year. But I can try to look it up for you.
That's okay.
They were, yeah, because they talked about it at one of the water management meetings that kind of happen regularly. So like I said, I think it's kind of public.
Okay.
So we can find it.
also wastewater is in similar work, but Dan and Shannon, they have a project where they're looking at population less than 10,000 those wastewater. I think it's about 300 or
10,000 is the cut.
10,000.
Less than 10,000.
How many That's very good.
We're supposed to do 20, I think we're up to 17 now.
We find a lot.
Probably less than what we get in the larger cities, but it's still there.
We don't have much manufacturing.
Right, yeah, that was one of the things we tried to tease out was the industrial sources, but
Yeah, in Nebraska, mostly it might be metal.
I bet it's mostly consumer
Electroplating.
products that are introduced into the system.
Even for urban areas, it's like food packaging can be one,
Yeah,
and electroplating. Electroplating is actually one of the major ones in most places.
Food packaging only in Norfolk, I guess. That's a bigger than 10,000, so you probably not, yeah.
Well, I appreciate all the great discussion, everyone. We are over time, so for the sake of that, we'll close it there. But let's thank Nirupam again for his presentation.